Today, I'll be talking about extending neural network verification tools to nonlinear systems through the use of overapproximation. So, neural networks can do really impressive things, like be trained to drive cars in less than a day. This video on the right is from an earlier project of mine where we trained a car to weave around other simulated cars in an afternoon. But neural networks can exhibit unexpected behavior because they have a lot of parameters and they're trained from data. If we're going to use neural networks in safety critical applications, we need guarantees of reliability. I'll illustrate here the specific kind of failure that we're worried about. So on the left, the top left, we have a 2D visualization of a neural network that's been trained to represent an aircraft collision avoidance policy for two aircraft that are flying towards each other. We've sampled points and plotted the recommended pilot actions, strong right, weak left, etc. And although the boundaries are a little mushy looking, the sample points all appear to have reasonable advisories. But if we zoom in between the sample points, there could be an erroneous clear of conflict advisory that could tell our pilot to keep flying straight and put it in danger of colliding with the intruding aircraft. This is the kind of network behavior that we want to guarantee that we don't have. There's a lot of work that uses testing to find failures in neural networks and other black box systems. And while it can provide important information about whether a system generally behaves as expected, like for example, if this function here generally lies within the green range, it can provide a formal guarantee of safety because you're sampling at discrete points. You might miss some of these peaks or valleys and think your function lies entirely in the green region when it doesn't. Fortunately, there's a growing body of work on neural network verification. This is from a 2021 survey paper that has 17 different methods. Neural network verification can actually prove that a property holds over a continuous input space, rather than just showing that it holds at sampled points. And if a property doesn't hold over a continuous domain, it can return a counterexample, like I've shown here on the bottom right. However, the current neural network verification literature has its own limitations. Generally, verification is always with respect to a specification. For current neural network verification approaches, this means that we have to specify the input set and the set that we'd like the outputs to remain within. But if your network is part of a complicated real-world system involving nonlinear functions, like for example, if it's driving a car, specifying these sets X and Y may not be straightforward, and the sets may change over time. Speaking of nonlinear functions, formal reasoning about them is difficult in its own right, as is neural network verification, from a worst-case complexity standpoint. So it goes to say that formal reasoning about systems containing both of them is challenging. But we think it's necessary as neural networks make their way into new and varied real-world domains. For this reason, my thesis develops methods to reason about systems containing both neural networks and nonlinear functions. Our first contribution is to drive an algorithm, OVERT, to compute optimally tight piecewise linear overapproximations for smooth nonlinear functions. Next, we apply OVERT to neural networks that have been trained to solve nonlinear inverse problems, where we're reconstructing the underlying state from a set of noisy observations. And finally, we apply OVERT to perform reachability analysis for nonlinear dynamical systems with neural network controllers. I'll talk about each of these in turn, and then I'll summarize. First, I'll talk about OVERT, overapproximation for nonlinear functions. So a large number of neural network verification methods, everything I've highlighted here in blue, relies on linear programming or mixed integer linear programming. These are optimization problems that can have linear constraints and a linear objective, and in the case of an MILP, real and integer valued variables. We'd really like to use linear programming or mixed integer linear programming because they're really well-studied problems, and there are a lot of commercial solvers that have had tons of money and time invested into them, making them fast and efficient. Using mixed integer linear programming for verification works like this. So we start with a fully trained network. And then we define variables representing the inputs and the outputs of the network. Then we encode the weights and biases of the network into constraints in the optimization problem relating the input and output variables. And then we search within this initial set X. We vary the input variables until we find a point in output space where the specification is violated. So to summarize, our goal is that we'd like to use mixed integer linear programming-based tools for neural network verification, and we'd like to verify networks that are part of complex, real-world systems involving nonlinear functions. But the problem is that nonlinear functions can't natively be encoded into mixed integer linear programs. So our solution is to find a new way to represent them, nonlinear functions, that is. What we do is we approximate them. But it's important that this approximation is done in a careful way, such that we can still make sound claims about the original nonlinear system. If we're going to go to the trouble of using formal proof-based methods, this soundness is important. The particular type of approximation that we use is known as overapproximation. So if a set of values that satisfy some set of constraints is shown in pink, we choose an overapproximation that captures a superset of possible values, shown in blue. If we prove that a property can't be satisfied by searching over the whole blue set, then it definitely can't be satisfied by searching in the pink set. So we do just this. We overapproximate nonlinear functions with piecewise linear bounds. There's been related work that performs formal reasoning over nonlinear functions, and these approaches also involve overapproximation. So there's work that uses incremental linearization, meaning linear bounds are used and refined as the algorithm progresses. There's also work that uses interval analysis, meaning that the nonlinear expressions are approximated with intervals. We introduce a new algorithm for producing optimally tight, piecewise linear approximations of nonlinear functions, which can be encoded into mixed integer linear programs. We use piecewise linear approximations like the first method here, because they're tighter than using intervals. Our work is different from the first method in that we construct an optimally tight approximation over a specified domain from the beginning, rather than slowly building towards an approximation that's tight enough to solve the problem. In a later section of this talk, where we apply OVERT to neural network verification problems, we write an interface to the second tool listed here that uses interval analysis and compare the results. So next, I'm going to explain the specifics of how our approximation algorithm, OVERT, works. And in order to do this, I'll use a pendulum example. So consider the problem of controlling an inverted pendulum. The state is two variables, the angle, theta, and the rate of change of the angle, theta dot. There's also a control torque, U. And let's now take a look at how the update equation, which I've written here, will be approximated. So first, let's condense any constants into C1 and C2. Then the first step is to rewrite nonlinear multidimensional functions as one-dimensional nonlinear functions or affine functions. In this example, that means pulling out the sine term. And then the bottom line on the slide here is affine. The second step is to approximate each nonlinear one-dimensional function using piecewise linear lower and upper bounds. In this example, we create bounds for the variable v1.
Cool. Get it on the bound.
Can someone mute? Yeah.
Got it.
Thanks. Okay, yeah. Bounds that might look like this. And so what you can see here is that we've used the bounds to create a set that the function lies within. These bounds are tight to the function. In fact, optimally tight for a given number of line segments per region of constant concavity. Tight bounds are important. If we computed a loose box that fit around this pink set, like on the left, rather than fitting a tighter approximation, like on the right, we might be too conservative and say that a property doesn't hold when it really would hold if our approximation was more accurate. And if we have multiple nested approximations, or if we have multiple time steps, this looseness compounds. OVERT constructs bounds by minimizing the area between the bound and the function, which is the area shown in yellow. For the upper bound of a convex function, it fits a string of secants, and it optimizes the location of the tie points, x1 and x2. Here we have a 3-segment bound, but you can use any number of segments to get an arbitrarily precise bound. On the left, we have examples of upper bounds for convex regions, and on the right, upper bounds for concave regions, using different numbers of line segments. So to summarize, we introduce a method to abstract nonlinear functions with optimally tight piecewise linear overapproximations. A piecewise linear overapproximation can be encoded into a mixed integer linear program, which is our target neural network verification approach. And these methods allow us to verify neural networks that are part of complex systems. Next, I'm going to talk about verifying inverse model neural networks. First, what's an inverse problem? So at their core, an inverse problem involves trying to reconstruct some underlying state of the system from noisy observations. There are a lot of inverse problems that we would like to solve. These range from image reconstruction in the medical domain to state estimation problems in the aerospace domain. Throughout this section, I'll be using a real-world airplane fuel gauge as a case study. The fuel tanks of an airplane are typically located in the wings. And in our case study, there are pressure sensors placed throughout the fuel tank to measure the liquid level. And the task is to answer this question: how much fuel is left in the tank as the aircraft is rolling, pitching, and changing altitude? As you can imagine, this involves a lot of nonlinearity between the mapping from fuel mass to pressure measurement. So how do we solve nonlinear inverse problems? Well, unlike the linear case, there's no general closed form solution. And if you have a many-to-one mapping, the inverse is not well defined. There are Bayesian approaches to estimate a distribution over likely state of the system, but they also don't usually have closed form solutions. There are sampling-based Bayesian approaches, but they also have their drawbacks, such as being computationally intensive, in our experiments taking up to 25 seconds for a single query. They can have convergence issues, and ultimately, they provide a statistical guarantee, but not a formal guarantee that the estimate is correct. For example, something like 99% of the time, the worst error is X with Y% confidence, rather than 99% of the time, the worst error is X. So neural networks provide a compelling solution for solving nonlinear inverse problems because they can be trained from data, they can invert arbitrarily complex and stochastic forward models, even containing many-to-one mappings, and they, for our experiment, seem to perform well. This graph should look like y equals x. On the left, we have Bayesian inference, sampling based. In the middle, we have linear regression. And on the right, we have a neural network. And we can see that the neural network does the best. However, this does leave us with a new problem. Neural networks don't have strong theoretical guarantees. So testing is always an option, but here we have some plots that came from an error that we actually made while working on this project that I think demonstrates how testing can be unreliable. So what we did is we accidentally trained an inverse fuel gauge model on regular grid points, and then we evaluated the model on regular grid points. And the error was pretty low. Note, the only thing that matters on these plots is the range of the error. But then we realized what we did, and we evaluated the model on uniformly randomly sampled points instead, and in the plot on the right, and the error was much worse. This meant the model had overfit to the regular grid points, but we didn't know it had overfit when we were using the wrong testing distribution. Verification approaches aren't susceptible to this kind of misleading result. So, what can we do to ensure the reliability of an inverse model neural network? Well, there have been some previous approaches. There's an approach that has used compared a one-layer neural network to a table using Lipschitz constants computed on a grid. And while this does provide formal guarantees, it's not scalable due to the use of gridding. It compares to a table rather than the true nonlinear model, and it's limited to one-layer sigmoid networks, whereas we're interested in bigger networks than that. There are also methods that can produce probabilistic guarantees using sampling, but again, not the formal guarantee we're after, and they can also be computationally intensive. Our solution is to use mixed integer linear programming-based neural network verification. So the central idea is that we use OVERT to overapproximate the nonlinear forward model with piecewise linear relations. And then because we use a ReLU-based inverse model neural network to go back from pressure sensor measurements to fuel mass estimate, now both the forward model and the inverse model can be encoded into the mixed integer program. The high-level idea is that we perform this verification offline, and then we use the results to determine if the network satisfies the necessary requirements to be used on board. Our work is the first work that we know of to apply modern neural network verification methods based on mixed integer linear programming to the problem of inverse model neural network verification, and the first which is able to produce formal guarantees for nonlinear stochastic forward models. So speaking of stochasticity, how do we handle it? Well, additive noise terms can be handled by adding an additional variable to the mixed integer program, but the mixed integer program requires a bounded domain for every variable. Our solution is to set the domain to, for example, 3 sigma, and calculate the mass of the joint distribution of noise that this covers. We can then say that the property holds, for example, if we have 2 independent variables with Gaussian noise at 3 sigma levels, this corresponds to 99.46% of the joint distribution. Okay, so now that we've encoded both the forward and inverse models, as well as the noise, what kinds of properties are we proving? Well, the first kind of property that we can prove is we can test whether the estimate of the reconstructed fuel mass is within some error tolerance, or we can solve for the maximum deviation between the inverse model's estimate of fuel and the true value. To demonstrate what an approach like this looks like, here's some results for the fuel gauge problem, where we calculate the maximum error between the inverse model estimate and the true value of mass in the fuel tank. There are several independent variables, but on the right, we show how the maximum error varies as a function of roll and pitch of the aircraft. Our method doesn't inherently require gridding the domain. Instead, we could produce a single maximum error estimate, but we grid the domain here in order to demonstrate how the error varies as a function of roll and pitch. The idea is that an engineer could use information from this plot to possibly redesign the system or retrain the network. They might look at that bright yellow spot of high error and collect more data from that region. So this plot characterizes both how the inverse model neural network is performing, as well as provides a meta-analysis of how well our method is doing. So our method computes a verified upper bound on the error of the inverse model because we're using overapproximation. This plot demonstrates that our upper bound is tight. The bottommost curve is a lower bound on error created with uniform random sampling. The curve in the middle, which might be hard to see, is also a lower bound created by passing the optimal points found from verification through the true nonlinear model. And you can think of this sort of like adversarial sampling. And then the topmost line is the verified upper bound. So the true maximum error lies between those two top lines. So it shows us that the network is not doing amazing, but our verification method gives us an accurate estimate on the performance of the network. We also demonstrate our methodology on a 2D robot localization problem. Here we have a robot that's trying to estimate its XY location using 2 range measurements, like shown in this little picture on the left, with the measurement model on the bottom. And on the right, we show the maximum error between the robot's true location and its estimated X position. And we can see here that the network is having trouble resolving the X position on the bottom, where it's yellow, And our conclusion is that it's due to the geometry of the problem. And so looking at a plot could help an engineer decide that maybe they should add stations to the top right and left corners of the room to make the estimation problem easier. We also assess how close the verified bound is to the sampling bound for this problem. Here we see the gap between the verified bound and adversarial sampling is larger than between uniform random sampling and adversarial sampling. We think that this is due to the fact that uniform random sampling is able to do pretty well when the state and observation domains are both only two-dimensional, as opposed to the fuel gauge problem with a four-dimensional state space and 12-dimensional noisy observation space. So to summarize, our goal was to verify a neural network that reconstructs state from a set of noisy observations. Our approach was to encode the nonlinear forward model and the inverse model into a mixed integer linear program. And this is a summary of the type of results that we can produce. Next, I'm going to talk about using OVERT to perform reachability for nonlinear systems with neural network control policies. So the goal of a control policy is to direct a dynamical system to a desired state or set of states. Like, for example, in this video, we trained a controller to weave between cars. And we did this in an afternoon, which demonstrates the power and flexibility of deep learning. Most approaches to autonomous driving cannot be implemented in a day. As a result of demonstrations like this, deep learning and deep reinforcement learning have seen increasing use for control. But verification of a neural network acting on a nonlinear system repeatedly over time is much more difficult than single-shot verification. To contextualize with respect to the neural network verification model that we defined earlier, if we're using a neural network as a feedback control policy in a loop like this, how do we define a set Y that we would like the control outputs to lie within, such that the system has the desired behavior many time steps into the future? Well, the short answer is that we don't really want to define sets in control space. I'll use an example to explain why. So say let's consider an automated driving task like this, where we have a neural network controlling the blue car, the steering angle psi, as a function of relative distance, x and y, to the yellow car. Using existing approaches, we can verify what we call an open loop property, like ensure the commanded steering angle produced by the neural network is never more than 90 degrees, which translates to ensure the car never swerves. But it doesn't tell you about the system behavior when the control policy is applied repeatedly. I would argue it's more informative to verify a closed loop property, like the vehicles don't collide. Because the blue car could still slowly drift into the other lane, even if it never swerves. And here, no collision is written as magnitude of the relative x distance must be above a threshold, and same for relative y distance. Also, note that this property is expressed in terms of state variables, not control variables. And proving a closed loop property like this requires modeling the dynamics of the car under the neural network control policy, which, as you can see here, for even the simple system, the dynamics are nonlinear. There isn't a lot of work that addresses closed loop properties of nonlinear systems with neural network controllers, and my work addresses this gap. Our approach is to perform reachability analysis. So for a closed loop system, the reachable set at time t is composed of all possible states the system could visit at time t. A reachability problem reasons about this set of states reachable over time and whether it intersects with an unsafe set or reaches a goal set. Other researchers have explored reachability analysis for neural network control policies. So first, I'll discuss work that's adjacent, but solves slightly different problems than what we focus on. The first category of work focuses on linear or piecewise linear system dynamics, which can't treat the smooth nonlinear systems we're interested in. The second adds the ability to analyze systems with polynomial terms in the dynamics, but we'd like to be able to handle a broader class of nonlinear functions. The third focuses on continuous time dynamical systems, which are fundamentally different than the discrete time systems that we focus on. And there's work that focuses on neural networks with sigmoid activation functions, whereas in contrast, we focus on ReLU activation functions, which are widely used. And lastly, there's work that focuses on partitioning. Intelligently partitioning the domain that we're verifying over can improve most methods, regardless of the class of systems that the internal solver can handle. So we see this as complementary. Next, I'll talk about some work that's a little bit more closely related. That is, work on verifying ReLU neural network controllers for discrete time nonlinear systems. There's work that approximates nonlinear dynamics with a neural network. And if the approximation is neither an underapproximation nor an overapproximation, it doesn't allow sound claims about the original nonlinear dynamics. There's also work that uses hybrid systems reachability tools, and while we compare to this work later on, it has a couple of drawbacks. The first is that it scales poorly with the state dimension, and the second is that this work in particular computes explicit reachable sets at every time step, which leads to a loose overapproximation and the need for partitioning, which often scales poorly in the state dimension. Lastly, there's work that performs reachability analysis for aircraft collision avoidance systems. This work uses interval arithmetic and derives custom bounds for the specific application domain. The bespoke nature makes it difficult to apply to new problems, and interval arithmetic can be loose, which then requires partitioning and again scales poorly in the state dimension. Next, I'll explain our approach to verifying closed-loop properties of neural network control policies for nonlinear systems. First, I'll give a high-level overview of our algorithm. The first step is to overapproximate the dynamics using OVERT, which might look something like this. Next, we unroll the closed-loop system, which is now all representable using piecewise linear constraints. Finally, we encode all of these constraints into a ReLU neural network verification tool in order to prove properties about the system. In our implementation, this neural network verification tool is a mixed integer linear programming solver, but our approach could in theory be implemented with any tool that supports piecewise linear functions efficiently. Okay, so now that we have a high-level idea of what's going on, what kinds of properties can we prove? Well, consider again the inverted pendulum system. We can check what are known as invariant properties, like, is the angle greater than negative 10 degrees for 10 time steps? Or we can ask if a property eventually holds, like, does the pendulum reach the set negative 1 degree within 10 time steps? These two types of properties allow us to solve reachability problems, where we want to answer questions about avoiding unsafe sets or remaining within or reaching goal sets. Okay, so to recap, we have a high-level overview and we know what kinds of properties we're trying to prove. How do we actually go about proving those properties? Well, there are two different methods that we can use to prove these properties. These are solving feasibility problems and explicit reachable set computation. They can both prove both types of properties, invariant and eventually true. Solving a feasibility problem involves less overapproximation, but explicit reachable set computation gives you intuition about how the system is evolving and why a property might be failing. We implement and test both of these methods. Common to both of them is that, you might have guessed, the closed-loop system is encoded as a mixed integer linear program. We have variables to represent the state of the system at each time step, as well as each control input, and we add constraints from the dynamics in the neural network to define how the state evolves and how the control is computed. We also have to constrain the input set X. If we take the approach of solving a feasibility problem, what we do is we add a constraint to the optimization problem, the complement of the property, which you can think of as the opposite. The solver then searches to find a feasible solution. If it finds one, then it means the property doesn't hold everywhere. If it can't find a place where the property is violated, then it holds. A visual representation is what's going on is shown on the right. This gray shape represents the implicit reachable set in theta dot space for our pendulum. And then we have this separating hyperplane on the right showing where the property doesn't hold. In this example, the intersection of the implicit reachable set and the complement of the property is empty. So no feasible solution will be found, and it will conclude that the property holds. Performing reachability analysis using this method has the advantage of having no explicit dependence on the number of state variables. Although, in theory, the worst case number of activation patterns in the neural network controller is related to the state dimension. The second method that we can use to solve reachability problems is explicit reachable set computation. In this method, we explicitly find the reachable set at the next time step, and then we do set intersection to see if the property holds. We compute the explicit reachable set by solving two problems for each state variable. For example, maximize theta and minimize theta. This gives us a hyperrectangle over-approximating the reachable set. Performing reachability analysis tells us how the system is evolving, but over-approximating the set with a simple geometric shape like hyperrectangle incurs a lot of looseness. In fact, if you continue to compute the reachable set one step into the future using the previous step, that is compute t plus 1 starting from t, which is what we call the concrete approach, this looseness compounds. It makes your estimate of the reachable set less accurate and less useful. One solution is to partition the input domain and compute explicit reachable sets for each subdivision, which some of the related work does, but this scales poorly. Another solution, which has appeared before in the formal methods literature, is to perform what we call symbolic reachability. In symbolic reachability, we compute the reachable set at time t equals 10, for example, beginning from times t equals 1 in a single solve. We do this by unrolling the closed loop system for 10 time steps and adding all of these constraints to the optimization problem at once. Symbolic reachability is slower than concrete, but it produces tighter sets. We can see in this plot the symbolic reachable set after 10 time steps in red is as tight as it can be for having a different template shape than the empirical reachable set in orange. But it takes 10 minutes instead of 4. And importantly, using symbolic reachability, the problem will stop being tractable if the horizon gets too long. The optimization problem will just get too large to solve. So what we'd like are both of these attributes, tight reachable sets and fast computation. As a result, we introduced the idea of hybrid symbolic reachable set computation. This plot shows rectangles approximating the reachable set of a cruise control problem. And here I'm showing a 2D slice of a 6D state space. So we start over there on the right, time t equals 0. We start over there on the right, and you can think of the purple as the true exact reachable set. We compute these pink one-step reachable sets until the approximation gets too loose. And then we compute a symbolic set from the initial set to the current time step. And you can see the pink sets pinch in to touch the purple. Then we repeat this process. We again compute one-step pink concrete sets until they get too loose. And then we compute a symbolic set from the last pinch point to the current time step. As you can see from this plot, this hybrid symbolic approach produces sets that are pretty tight compared to the purple, and the increase in time is not terrible. More importantly, though, because we do this sort of sliding window approach, where we do symbolic computation only from the last symbolic set to the current time point, the computational difficulty of computing symbolic sets doesn't increase strongly as a function of the time horizon. With one important caveat: if your system is diverging and the reachable sets are growing, the computation will slow down. But this is due to a property of the system and not our reachability approach. So we also compare our method to some baselines. Here we compare to the NNV tool, which we adapted for use with discrete time systems, and we prove an invariant property for the pendulum problem. Because NNV uses concrete reachable sets at every time step, the reachable set approximation explodes. The left is a zoomed in image of the right so that you can see the reachable sets computed by our tool, which are 2 orders of magnitude tighter than the sets computed by NNV in green. You may not even be able to see the pink dot at the center of this plot on the right. Here we compare the speed of both of our methods, feasibility and hybrid symbolic explicit reachable set computation, to 2 baselines. The first, which serves as a comparison for feasibility, is a finite precision SMT solver called DReal, which is designed for nonlinear systems, but not for neural networks. The second is NNV. So we test two problems. DReal times out in one instance and is 2 to 3 orders of magnitude slower in a second. And NNV also times out in one instance and is both an order of magnitude slower and unable to prove the chosen property. So our conclusion is that a tool designed specifically to handle nonlinear functions and neural networks does better than those that aren't designed for that. So scalability is often an issue for formal verification tools, so we evaluated how our method scales. Each dynamical system has qualitatively different dynamics and different safety properties, so we don't think it makes sense to compare across problems. But for each dynamical system, we train neural network controllers of different sizes, and we plot computation time versus number of ReLUs. On the left, we have explicit reachable set computation, and on the right, we have feasibility. Our takeaways from these plots are that 1, most of the problems take less than 20 minutes to verify. The exceptions are these red points on the left plot, which come from one of the problems and approach 18 hours in compute time. Interestingly, solving the feasibility framing of the same problem, the red line here on the right, takes less than 9 minutes. While these plots don't have enough data to make a firm conclusion, the straight lines on the left plot suggest that hybrid symbolic reachable set computation, at least for these examples, has polynomial time complexity between y equals x to the 1/2 and y equals x to the 4th. The feasibility framing may have exponential time complexity, that's a function like y equals 2 to the x, but there isn't quite enough data to tell. However, the feasibility algorithm that we use in these experiments doesn't have the opportunity to perform resets like the hybrid symbolic reachable set algorithm does. Despite that handicap, the feasibility framing was faster than the explicit reachable set computation for all of these problems except for one, despite possibly scaling more poorly. Last, we test our approach on a system that's closer to real world, a 6-dimensional quadrotor model. So the goal is for the quad to fly to the right while avoiding this red obstacle at the origin. We first solved the problem, the control problem, using nonlinear MPC, and then we trained a neural network from these expert action labels. A key reason that people are interested in learning for control is that nonlinear MPC can become slow. In our case study, executing the trained network was 400 times faster than the nonlinear MPC, 40 milliseconds versus 1/10 of a millisecond. We can see in this plot on the left that the verification believes the system is unsafe. The red and pink sets overlap, but this seems reasonable given that the purple set of true trajectories comes really close to the red obstacle. And on the right plot, we have a time history of 15 time steps. So to summarize, our goal was to prove safety properties for neural network controllers of nonlinear systems. Our approach was to perform reachability by overapproximating the dynamics using piecewise linear constraints, unrolling the closed loop system, and encoding everything into a mixed integer linear program that we can either solve a feasibility problem or explicitly compute the reachable sets. And these are what our results look like. Finally, I'm going to summarize what I've talked about and discuss some future work. So here's a summary of my contributions. The first, a method to construct optimally tight approximations of nonlinear functions. The second, a method for verifying inverse model neural networks. And the third, a method to perform reachability analysis for discrete time closed loop systems with neural network control policies. Together, all of these things bring us a small step closer to being able to use machine learning on safety critical systems. So the first area of future work that I'm interested in is approximating the reachable set with polytopes that are more complex than axis-aligned hyperrectangles. While this may seem like a simple strategy, shape mismatch of the reachable set is responsible for the majority of the overapproximation error, even when dealing with nonlinear dynamics, due to the fact that the bounds we use from OVERT are so tight. I'm also interested in infinite time guarantees. The methods that I've talked about allow reasoning about the safety of a nonlinear dynamical system with a neural network controller over a finite time horizon. It's useful to be able to say the speed we're controlling will not crash into the vehicle in front of it for 50 time steps, but it would be more useful to say that it will never crash. There are stronger guarantees available, like Lyapunov and contraction certificates, for more classical control strategies, and I'd like to bring these to neural network controllers. There's some recent work exploring this that has learned and verified Lyapunov functions for neural network controllers and learned and verified contraction metrics. We started exploring learning and verification of these certificates for neural network controllers of general nonlinear dynamical systems. And I'm excited about this direction of work. And finally, I'm interested in verification of uncertain models. So in this talk, I discuss verification of models that contain inherent stochasticity. But I'm also interested in exploring verification where the uncertainty comes from the fact that the model is not fully known. This is often the case in ecological models, biological models, and when interacting with people. Scientists will often fit mathematical models from data that appear to work well, but as we discussed earlier, verifying with respect to a learned model doesn't provide any guarantees, and I'm interested in exploring ways to bridge this gap.